Frivaldsky, and the presentation is combining DVR and UPS techniques for an interruptible supply of ultra-sensitive nonlinear appliances. So please.
Come on.
Please share the screen.
Yeah. Hello?
Okay.
Hello?
Hello. Okay. Please.
Can I start? Thank you, Chairman. Good morning, ladies and gentlemen. My paper, thank you for introduction. And my paper deals with an application of combined techniques of dynamic voltage restorer and uninterruptible power supply, which makes possible both of the short time watch sex compensation as well as longer power supply interruption under the simultaneous operation of equipment and the network. That means parallel operation. The combined techniques is enabled mainly using an instantaneous voltage sex detection, quick bit bidirectional over switches. Also, it needs a very fast control method which can provide a voltage recovery for phase-sensitive loads during several calculation steps, so the deadbeat regulator is used. Such a system compensated even the influence of nonlinear loads on the power supply network. Topics of the paper is normal, and on the end of presentation, I will show you the modeling and simulation results, and also the experimental results. The first slide shows us the block diagram of a DVR restorer. There are normal operation full line and restoring operation dashed line. The next one is the circuit schematics of a DVR. So it's known, I hope, for the more people. And this is the principal block diagram using UPS system. So it's classical, but during the step changes with the over switches between network and UPS, sometimes is problem with transient of the current and voltages. You can see on this picture. When the step change is from 0 up to 100%, this is the problem. So the new concept block scheme is shown on these slides. You can see in the right on this slide. And as I said, the UPS will use the deadbeat controller, this bottom figure. So when we need to substitute of the both properties of DVR and UPS systems, we can, it is enabled, but mainly by the instantaneous voltage sex detection, quick bidirectional over switches, and the instantaneous, very fast control method of the output voltage, as I said. What brings such a combined scheme? Instantaneous voltage sex compensation, minimizing of transient phenomenon, and improving of reliability regarding to mean time between failure by some order. So regarding to determination of the instantaneous voltage, we have used the DQ coordinates because in DQ coordinates the voltage is constant. It's written on this figure, and this equation is very clear. Vd plus Vq is the constant. Also, V alpha and V beta is constant also. Okay. So this is the circuit scheme of VSE inverter used in UPS systems. You can see PWM inverter, LC filter, and nonlinear load here. Nonlinear load, it means that it's a rectifier with capacitive filter. This is written capacitive rectifier. So model of VSE inverter is well known. This is the equation, this model in block scheme. So now we will talk about shortly about current loop control. This scheme, complete scheme, and a simplified scheme is on this bottom figure. As you can see, we have used that bit controller. So transfer function in operator mathematics is shown on these equations, and the transient function in Z transformation is written here. So we can this model of the current controller is very easy, and we have simulation the operability of the current controller. And as you can see, in two computation steps, the current will be regulated. Yes, these main benefits of the deadbeat controller. Voltage control loop is rather complicated, but it's possible also use the simplified control loop in the bottom part of the slides here. But some problem is that the in the numerator of the transfer function there is some zero. After parameterizing, it's here, and this is show that the compensation of zero of transfer function is used at this block scheme here. So then we can the final transfer function you can see here, and the denominator compared to the standard second order transfer function here. So by comparison we can determine the gain of the transfer and also integral integral time constant here. We can use also dot relation here. So after this, we can simulate the whole system's new concept. So this is a simulating model of VSE with LC filter and nonlinear capacitive rectifier here. And this is system parameters and control system parameters here. Output power, switching frequency, and so on. Load. So now I can show you the result. This experimental parallel operation of the new UPS devices with network. So you can see the current from network, current from UPS are in parallel is the same, 50-50%. The next simulation results show the grid network disconnect in the maximum voltage, resistive load, inductive load. So this is simulation. During simulation, that bit controller is a very fast activity. You can see here in the time 0.045 milliseconds here and here. The next figure shows the change of the load from 0 up to 100%. Linear resistive load. There is the simulation, this experiment. You can see that experiment is very similar to simulation result. Grid disconnect is in this time, as in previous, in this 45 milliseconds about. The next is linear inductive load, and also the from change load change is from 0 up to 100%. So it's simulation result, experiment result here. And I think it's the last simulation and experiment results. So this nonlinear load, parallel operation grid and the new UPS concept system. So you can see in this time, as previous in 45 milliseconds here, the grid is disconnected. So the voltage is slightly disturbed here, but THD total harmonic distortion of the voltage is very good, is about 2%. This after disconnected this network of the. So this is the conclude of my presentation. The combined technique of dynamic voltage restorer and uninterruptible power supply, providing compensation for the short-term voltage shifts as well as longer network interruption have been shown. Comparison of simulation and experimental results show a good agreement and a good quality confirmed also for nonlinear loads. The difference between the measured and simulated waveform reaches just 2.15% regarding to THD, total harmonic distortion. This all is enabled mainly by instantaneous voltage detection using DQ method, quick bidirectional overswitches, and very fast, nearly instantaneous control method of the output voltage. So it's all of my presentation. Thank you.
Thank you. Well, actually, Mr. Chairman was disconnected because of the problem in electric engineering area. Something went wrong with electricity, and somebody tried to interrupt our session. So, what would you suggest for conference participants and for users in case to avoid longer interruption, around 1 or 2 hours? If we have something wrong, something bad with electricity, with power supplying.
Okay, I think that you should continue your role as a chairman. That's okay.
Yes, so definitely, it is not a problem.
Yeah.
So, do we have any questions from participants?
May I have a questions? One.
Yes.
That's really good, very interesting paper and good approach to this. That's very important things, particularly in the very sensitive nonlinear loads. Have you already applied for electrical motors of some your devices to check if everything is okay? if, for example, if frequency is being changed, since we have sometimes in the mining industry, we have electrical motors with regulation of a speed, and the frequency is very low. What about if the frequency is low? It will work efficiently or no?
I think it's possible. The frequency, you can see on the experiment, the frequency is still the same as previous after the grid connection. So it's possible to connect also some synchronous servo motor and so on.
Okay, thank you very much. Thank you very much. Very interesting.
Thank you.
Okay, thank you for the presentation. And I would like to invite the presenter. We have substitution. The presenter will be Gergana Vacheva, and the presentation is named Mathematical Model for Determination of Energy Cycles in EVs, electrical vehicles. Yes. So
thank you. Thank you, Mr. Chairman. Just a second to. Okay, is it visible?
yes, just press
Okay.
Excellent.
So my name is, thank you. My name is Gergana Vacheva, and today I will present you our presentation, which is entitled Mathematical Model for Determination of Energy Cycles in Electrical Vehicles. I'm from Technical University of Sofia, Bulgaria, and so today we will present you this title, a short, brief one of the presentation. I have some introduction, the mathematical modeling, the results, discussion, and conclusion of this paper. So as an introduction, as you can see, the electric vehicles are those who the main energy source, it could be fuel cell or rechargeable battery or supercapacitor. They are increasingly used in accordance due to the increased environment requirements. This is a result of progress in the field of mobile electricity sources and the use of efficient electronic converters and control systems. For technical and financial reasons, the number of electric vehicles is significantly smaller than those which is powered by liquid fuels. And this is the main reason for the research of this problem, which is the high cost of the battery, the hydrogen components, and the supercapacitor, and also the lack of the infrastructure for charging electricity of hydrogen. Here is presented the table 1, in which is the characteristic of the used in this paper electric vehicles. Here we have Nissan Leaf and Tesla S, which is provided by the manufacturer. And here you can see the different parameters, the years of the when it's produced, the different type of the electric vehicle aerodynamic coefficient, which is a little bit changed between the two electric vehicles. So the rolling resistance, the mass of the vehicle, and also the mass which is produced by the different cycles, driving cycles, which is provided by the European Commission, and also the torque, maximum power, maximum speed, which can be obtained by the different type of electric vehicles, the G ratio, which is used, the friction coefficient, and also the wheel dynamic radius of the tires. And here we used, which is one basic equation. This is the mathematical models, which is implemented in MATLAB Simulink, and we used this equation to calculate and verify the obtained data, which is provided by the manufacturer. Here we have equation which describes the dynamic of the vehicle movement. So this is the second law of the Newton. Here we have the velocity, the aerodynamic force, friction force, and traction force. So here with this equation, we calculate the tractive power, which is FA, it is necessary to take into account the maximum torque of the vehicle and also the maximum power and their limits. So here in this equation, we have some limits, which is about this. This limitation will be considered further, but in both cases, it's necessary to make additional check that the traction force is less than a DC force between the road and the vehicle. And here we have some constraints, which is presented in figure 1. Here we have the curve of the maximum force of electrical vehicle. So here we have some constraint by maximum power and some constraint by maximum moment. This the first one defines the line when the maximum moments become equal to constant, and the second one defines the maximum power. So here we have the speed, which is the switch speed, and the maximum speed that we can obtain. Maximum traction force is applied to achieve a maximum speed of 10 seconds. At this moment, the pulling force is limited by the distance speed. After reaching this speed, we will go the tractive force, and after that is limited by the condition of maximum power. So here is the equation that describes this constraint. With these two limitations, we get the switching speed, and the maximum tractive force is described with these two constraints. For when is minor than the switching speed, and when is constrained by the power of the electric vehicle. So here is the model which is realized in MATLAB Simulink. So here we can obtain we can calculate the acceleration, the velocity, and also the road, which is the distance of the road, which is made for this 10 seconds. And here is presented the results. So we have the traction force with Nissan Leaf. Here we can see that we obtain about 4,200 newtons, which is the force. And here in the second figure, you can see the curve which describes the acceleration, which is obtained for this power, just for the time which is nearly close to the that which is given by the manufacturer of this type of electric vehicle. Here we have the velocity, so the speed, which is from 0 to 100 km/h, and also the distance for this 10 seconds is presented. And here we are made our results with a reference of two driving cycles. We used as a reference VOTC, which is class 3 and also class 2. This is a test procedure which is provided by the European Commission, which is used for evaluation of fuel consumption and carbon emission. Here in the first figure, we can see exactly what is the time and this type of procedure. So here we have multiple acceleration and braking modes for the time of 1,800 seconds. And here we can see the acceleration which is obtained for this exactly this type of cycle, and also we used this type of cycle to make some evaluation of the power of the electric vehicle, the electric motor, with this equation. So we have the energy, and also here is for this type of cycle. Here is presented another one, which is similar, but you can see we have, this is class 2, and we have a different profile of the acceleration and braking mode. And so you can see that we obtain different results for the acceleration and also for the power. And also we made some calculation of with this method, with the previous equation. We calculate the total energy which is used in this type of driving cycle. And as a discussion, I can say that with the accomplished research of the dynamic of the electric vehicles, which is simulated with different test procedure, it can be observed the total sum of and energy in the presented scenarios. And there's a significant difference about the two of them. The duration of the test procedure is also with a different time. It can be observed that the second scenarios, the maximum velocity significantly decrease. These reasons lead to the conclusion that the different test procedure has high influence to the total energy which is produced by the electric vehicle, the energy that can be stored necessary for the design of the system of power converters, and also with the management of energy storage devices for providing the adequate operation of the entire propulsion system. And as a conclusion, I can say briefly that the realized mathematical model of mechanical structure of electric vehicles provides the study and research of multiple operating modes, such as accelerated a vehicle dynamic mathematical model. The maximum speed is achieved through a more in-depth study of vehicle performance, and the consideration of each subsystem constituting the structure of electric vehicles would help to create a model which describes the different modes of operation, and with defining the selection criteria for converters such as input voltage, output voltage ripple, load current ripple. Operating frequency of the converters helps to determine the operating modes of the low loss converters, which leads to increasing the millage. And on the other side, the type of test procedure has significant influence of the energy demands of electric vehicles. And with improving this methodology, represent.
Thank you for the presentation. Oh, it seems okay. The presenter is still connected. Okay. So
I'm sorry for.
Sorry, we didn't hear you clearly. Okay. Do we have any questions?
Do you hear me, dear Darius, now?
Yes, everything is okay.
Can I continue with the chairing of the session?
Yes.
Okay. Dear Gergana, thank you very much for your presentation, and sorry for my absence for the first two presentations.
It's not a problem.
How goes the thing now with questions? Somebody of persons who is online can ask you somewhat related to your work. No questions. Thank you very much, Gergana. We will continue with
questions. Maybe I can ask one question, okay?
Yes, yes.
What about experimental verification? Are you going to somehow to apply it, or just do you have any plans somehow?
Yes, at this time we are not finished, but we have plans to use the two motors, which is traction motors, with two different DC converters. One of them which is bidirectional, and the other which is in the one side. And also to use a supercapacitor and the fuel cell as two dependent sources of for supplying the electric vehicles, and also to use the supercapacitor for storage the energy when during braking to regenerate the different time. But at this moment is not finished also the experimental
I see. Okay.
issue. Thank you.
Thank you very much for question and for the response. I think that was all. We will continue with the next presenter. The next presentation is evaluation of gallium nitrogen power transistor switching performance on characteristics of bidirectional DC-DC converter. And this paper will be presented by Michal Frivaldsky. Is presenter online or no?
Yes, I'm here.
No. Yeah, welcome.
Hello. So I have started to share my screen.
Welcome. Take your time and good luck.
Thank you very much. So my name is Michal Frivaldsky, and I'm from University of Žilina, Slovakia. Here we are dealing with the investigation of the power transistors from the evaluation of the switching performance point of view. And this research is also applied research, because instead of the evaluation of the switching performance, we also provided the implementation of the tested device within proposed DC-DC converter. So the content of the paper is as follows. So at the short introduction, we are discussing the evolution of the silicon transistors up to gallium nitride technology. Then we are discussing the influence of the switching frequency on the amount of the switching losses of the given transistor type. What we have done and how we deal with the experiments, we have used very precise PSpice simulation models. So we have been, it was possible to investigate the losses very quickly. And in the final, we provided the experimental verification of on the proposed bidirectional buck-boost converter. So, as I mentioned, we have selected the gallium nitride transistor type. I will skip one slide, but then I will go back. So this transistor is from the GaN technology company. They are using enhanced mode gallium nitride technology with the patented technology of the package. So on the left side, you can see the structure of this transistor, and on the right side is the parameters, the main parameters. So the transistor is suited for blocking voltage of 100 volts, and this will be enough for the target application, because the maximum is 24 if the boost mode of operation is considered. Also, you can see that given transistor type allows high current rating, and this is due to the fact that it is a transistor which is suited for automotive segment. Very important issue during the design of the gate driving system is this parameter. So the gate driver must be able to provide also negative gate voltage. So it is a little bit tricky to design such driver. Here you can see the evaluation of the switching energy on the value of the switching current, while both turn on and turn off energy are considered, and the characteristics are a comparison between experimental measurements and the simulation of the switching performance. So here it is confirmed that the simulation model, PSpice simulation model, has a acceptable accuracy, and for the parametric investigation, it is enough to provide the simulation. So you do not need to make a test stand in the laboratory and make the measurements if you obtain or if you have such precise and accurate simulation model. So therefore, we have decided to evaluate in parametric way the switching losses for the hard switch commutation mode. So there is no resonant switching. The circuit topology in PSpice is shown here. So as a blocking diode or freewheeling diode, we are using very fast Schottky diode. So there is no reverse recovery and there is no influence. You can see it here on the turn on performance of the transistor. This is the simulation model and the equivalent circuit of the evaluated transistor, and the parameters that have been has been changed are transistor current, switching frequency, and the voltage. There are two levels of the voltages because in one mode the converter operates as a buck converter, in the second one as a boost, so therefore two values. What is interesting is the values of the switching frequency. You can see that we have been testing almost 700 kilohertz of switching frequency, but this is normal if the gallium nitride transistors are considered. What is unwanted effect? You can see it here that there is a high voltage ringing during the turn off of transistor, and the value exceeds the allowable level of blocking voltage, which is shown in datasheet. It can be caused due to parasitic inductances within the circuit. So therefore, in practical applications, it is good to use some snubber circuit to reduce these spikes and to prevent transistor from any damage. So we have provided the parametric evaluation of the switching losses. So here you can see that there are turn-on losses and turn-off losses. The value of the frequency was changing, and also the value of the current. So it is natural that for the high currents, the losses are the highest. Also, the switching frequency is increasing the total value of the losses. What is interesting here is that the total losses for lower frequency, 500 kilohertz, is higher than for the highest frequency, 700. So from this result, and for 12 volts of the supply voltage, we can conclude that the gallium nitride has also a very good performance if the high switching frequency operation is required. The same tests have been done for 24 volts, and the results are also very interesting because we are reaching very good performance for the highest switching frequency. So here is the 300 and 700, and there is a very, very small difference. If we compare these results for the 24 volts and 12 volts, we can see that the supplying voltage does not affect as much the total value of the power losses. So the voltage does not have direct impact. The main impact is provided by the current and switching frequency. So now we have some overview in which, let's say, power loss level, the transistor can be operated. And then we have implemented these transistors in a proposed bidirectional DC-DC converter. So the equivalent circuit is shown here. So in one mode, the converter operates as a buck, in the second one as a boost. The converter was designed for a nominal switching frequency of 500 kilohertz. These are the output or input-output parameters. And the nominal power was 120 watts. On here you can see the experimental prototype, and the nominal frequency of 500 kilohertz is mentioned here due to design of the inductive elements, so the inductors or filtering capacitors. The proposed module consists of two boards. The horizontal is a motherboard, so here there is implementation of the control circuits and monitoring circuits, and the vertical one is the power board. There is a small heatsink located on the transistor, so there is no forced cooling, just the passive cooling. And here we are showing the experimental test stand. So for the evaluation of the efficiency of proposed converter, we have been using a spectral analyzer, and both boost mode and buck mode was verified. You can see that the converter is achieving almost 97% of the efficiency up to the 50% of nominal power. And for the nominal power, it reaches 95% of efficiency. So this slide is showing the same results, just in a better scale. And what was confirmed if the simulation analysis was provided, you can see that this curve is valid for 300 kilohertz. And for the higher switching frequencies, the converter has a much better efficiency. So this confirms also the fact that the GaN power transistors are suited for very high switching frequencies. So it is possible to improve the power density of the converters. So I think that that's all from the presentation, and I am open for discussion. Thank you very much.
Okay, thank you for your presentation. And for this, how to say, nice work.
Mm-hmm.
Are you online,
Yes.
Michael?
Yes, I'm here.
Yes. Okay, do you hear me? I think about that.
I can hear you, but
any question from other attendants of this group? No question. That's all, dear Michael. Thank you for the presentation.
Thank you.
Have a nice day. Bye.
Bye-bye.
Next presentation comes from China. The title of the paper is Exploration, Disaster Source of Mine Water by Electromagnetic Radiation. And this paper will be presented by Benyu. Do you hear me?
Yes, sir. Is okay? Hello? Is okay? Hello? Hi. Good morning. Good morning. Hello?
Yeah. You can start your good morning, of course. Do you hear me? Do you hear me?
Thank you very much. Yes.
You can start your presentation.
Okay.
Welcome, please.
Okay. Good morning, everyone. The title of my presentation is Exploration Disaster Source of Mine Water by Electromagnetic Radiation. My name is Benyu from China University of Mining and Technology. And my report outline totally contains 3 parts. The first one is the introduction of my research. The second one is my main research content. And the third one is my conclusions. And first one is the introduction of my research. Because the name of my university is China University of Mining and Technology. So here, the education and research focus on coal mining. However, mining safety is the first position. And generally speaking, in the coal mine, we have the following natural disasters. The first is the gas outburst and explosion. The second one is the coal dust output and explosion. And the third one is the mine fire. And the fourth one is the mine water flooding. And next is the roof exchange and rock outburst. And because in our university, we have different research team for research different natural disasters. My research team works focused on mine water flooding. The reason is that because as shows the figure, because the pressure of the earth is very high on the ground surface. So once exit of the water flooding happens, it will flood the whole coal mine tunnel during a very short time. So it usually results in serious casualty of mine lives and property loss. So this is my research purpose. And currently, and we have 2 masters popular in the coal mine for detecting mining water disaster. The first one is Transistor Electromagnetic master. And before in the maybe 2007, I do the report about 2 masters. The first one is TM master. This is the tunnel. Now this is the tunnel, and we put our equipment here. We can detect the geologic information from different directions, and from those geologic information, we will transfer those information to the resistivity of the command. So this is a figure shows we detect the distribution of the resistivity in the command, and usually low resistivity means it's water. So we can tell the mine, the geologist, maybe here is the water. They will using the other technique to make sure where water where it is the water. And the second method is the direct current method, and this is the tunnel. And we put the electrodes in the tunnel. By measure information, we can use those information to know if random of the heading geological information like here. So this is our our research result. This it means here the geological information is here. So we from those information we know if random of the heading where is the geological information. So this is two method is very popular, and in the command, our research team usually use those two methods. But today, I want to introduce another method. This is the geology models, and this is the COSIM, because this is the tunnel. Because usually when we cutting or drawing the coal mine, usually here or here will broken zone will formed, and those broken zones sometimes will develop into the mining water conductor path. So it is very dangerous for coal mining. And this is the first one. And the second one, because during the formation of those broken zones, here will produce electromagnetic waves. So so the purpose of our research is we try use the information from here to detect the coma geology information. And for example, this one, if some brick zone developed into like this, it will conduct the mining water, and it will result in the mining water flooding. So it's very dangerous. So next is my research content, and because this article properly is for theory research, so we use the forward modeling and the inverse modeling to show my research is it can be used for detect the mining water disaster source. Generally speaking, because this is a transistor, and this is the geologic anomaly. So this figure shows the electromagnetic propagator in the medium, and EI like this, EI, HI, and EI, it means the instantaneous wave, and ES and HS indicate the scattering wave. In fact, the electromagnetic wave exists in the medium with the form of the total wave, which means the total wave contains the incident wave and the scatter wave. Based on those ideas, we can use those formula, and finally, we will not interpret it in detail here. And finally, we will get this formula like this one. And my research for calculating the electromagnetic wave using this formula. And this is a simple model, and because during the formation of the break zone like this one, it will produce electromagnetic wave. Here we use 16 electron dipoles to stimulate the flexo produce electromagnetic wave, and this is the modeling result. So we compare those two, and we can see this formula can match this model very well. And this is a simple model. In fact, in combine, the model, the geological model, maybe like this one. This is the tunnel. When we combining, and it is possible in front of the heading, there will be a coal rock fractal will be found, and here, in fact, in my simulation, I how to say, this one can be say the transistor. It may be here. It will produce the electromagnetic wave. And then this is the model result. So we can compare two. This is the model. This is electromagnetic responses for this model. So we compare two figures. We can see it match very well. In fact, as I mentioned, because this fractal also it can produce electromagnetic waves. So we try use this one to detect other electromagnetic anomaly bodies. Like this one, if here is water bearing zone, maybe the water bearing zone is here. So we can calculate the responses, electromagnetic responses, this one or this one. So we can say, how to say, geology, electromagnetic geology models, coma geology, and is very sensitivity for those electromagnetic waves. Based on those formula forward modeling, so we can build a function like this. And this is one is we think is observed data, and this one is theory calculation values. So we can use mathematical method to get the arbitrary solution. It means we can from this iteration, many times iterations, we can get the distribution of the common geology electro is dielectric is we will get the solution arbitrary solution. A solution, it means is the distribution of dielectric constant. And last simulation like this one. This is the model. This is cosine. This is cosine, and this is the flex dose, and this is the forward modeling. And we calculate use this one, and by the how to say, by this function, we will get the distribution of the electric constant. So we can compare this to figure. This is my inverting result. This is the models. So from this one, from this inverting models, we can guess the distribution of the dielectric constant. And this result is our research, another team, they work used now. Our method compared with this one, we can locate the geology anomalous bodies in the command, but they just get the get the get the responses. So my master is good, is better than them. So next is my conclusions. The first one is that this is a model. This is a forward modeling. So scatter electromagnetic field responses is very sensitive for the coal mine geology. The second one, because this method from the other authors' research, but they use the smaller scale, but my research can use the a large scale. And the third one, compared with the method from the China State Key level of the coal resource safety mining, my research can locate the disaster source processively. So my method is maybe is better than that. That's all. Thank you.
Thank you very much, Mr. Su, for your presentation. We spent a little more time that was permitted, and we will continue with the next presenter immediately, without question. Thank you for your interesting presentation and work.
Thank you very much. Sorry.
Have a nice day. Bye. And the next presenter comes from Poland, and the title of the paper is Subjective and Objective Quality Evaluation Study, presented by Grzegorz Mieczysław Debita. Do you hear me, dear Mr. Debita? Yeah?
Okay, hello. Hello, can you hear me?
Okay, take your time and welcome.
Okay, Mr. Chairman, thank you very much. The title of the presentation is Subjective and the Objective Quality Evaluation Study of BPL PLC wired medium. The outline of the presentation is the short introduction to the problem, objective evaluation tests, there will be something about the noise measurement, narrowband transmission, BPL bidirectional voice transmission, and the subjective evaluation tests. And the last point is discussion and the conclusions. First of all, the BPL PLC technology is an alternative way to methods to use in signal transmission. The main advantage is the low cost of this application, because we can use the existing infrastructure to create the telecommunication network. Some problems is that the one to the note in this technology is in general sensitive to the environmental electromagnetic compatibility interference, but included. We are make some application in BPL PLC frequency range from 2 to 32 megahertz in a main medium voltage, the middle voltage network. It can to use not only to control environment condition, but most of all as a voice or image transmission medium, included so-called last chance in case of tilts and the mine disasters. In the fact, the middle voltage cable networks are theoretically the most resistant to mechanical damage. In this work, we have the test results of the signal transmission efficiency correlated with the efficiency of bidirectional voice transmission in 6 kHz mine cable network using the BPL technology. The measurements, both narrow of the half to 15 megahertz and broadband 2 differential modes frequency range, 3 to 7.5 megahertz. Tests were performed for both inductive and capacitive inductive coupling with measuring devices for PLC BPL cable modems. The test regarding the signal transmission efficiency in the middle voltage mining cable were carried out under real-time mining operating condition, taking into account about noise level in the cable and its loading with distorted current waveforms. The effect of the powering the cable on non-linear loads being the source of higher harmonics of both current and voltage was also explained. Firstly, we are make the noise measurements with two methods. One method of measuring the value of the waveforms level in the cable under non-linear load that show in the figure on the next slides. We are test carried out the both capacitive and inductive coupler installed on the cable supply in the point A in the mining. In this case, there was a spectrum analyzing and the resolution bandwidth was less than 1 Hertz. And during the tests, the cable supplied non-linear mining loads. For example, the motors with frequency converters. The effective value of distorted current was the approximate 18.4 amperes. And the harmonic content 3rd, 5th, 7th, and 11th in voltage was relatively small to that DHD value was with on half to 20.7%. And we will see that we'll see on the slide that is the picture where we have the spectrum analyzer on A is connected to the capacitive coupler, and on the second situation the spectrum analyzer was connected to the inductive coupler. And that is the noise measurement for the first picture to the capacitive coupler, and that is for the inductive coupler. Next step was the narrowband transmission. The configuration for narrowband transmission that will be shown to the next figure, to the next slides. The input signal frequency in the half to 15 megahertz range, with a constant amplitude of the 10 dBm power was injected from the generator And we are make the measurements in this connection. The first was the spectral analysis was connected to the capacitive coupler and the signal generator to the injective coupler. And the second situation was that the spectral analyzer was to the inductive coupler and the signal generator to the inductive coupler. And the results, the blue one is for the inductive coupler, and orange red one is for the capacitive inductive coupling results. And we are calculated the attenuation factor using the model. We are model all the cable for the two aspects, to inductive coupling and for the inductive and capacitive coupling. The first is for the inductive coupling. A second is for the inductive capacitive coupling. And we will see that the calculate attenuation is very closely to the measurement. And the last type of experimental was the BPL bidirectional voice transmission. We haven't specified the highest efficiency of the narrowband transmission for the test type of the medium voltage for 6 kilovolt cable. And we are used the frequency range between 2 and 8 megahertz. We are used two different modes using OFDM cable. Mode number 1 was from 3 to 7.5 megahertz, and mode 11 from 2 to 7 megahertz. And the test was carried out in an arrangement, and in the feature on the next slides, we will see for both capacitive and inductive coupling and inductive coupling for the BPL PLC transmission. And now we will see that how the network look like. The first is the master gate. In the modem was connected to the capacitive coupler, and there was the voice transmission server with the computer, and the slave gateway connected to the inductive coupler with the microcomputer as a client. And the second situation is we have changed in the coupler and we connected the master gate to the inductive coupler. And the results are shown at this table. The approximately bitrate transmission was for the mode 1 from 23 from 8 to 23 megabits per second. For mode 11 was 11 to 34 megabits per second. We can see that the transmission is not symmetrical. And we make some experiments, this subjective verification, compare the objective simulation and the measurements results in performed by the human individuals. To subjective assessment was carried out using biodynamic custom one handphones, and invited the group of 15 people aged between 25 to 35 years old, and the note of them had hearing distorted. each individual assigned that the quality individual in 5-step of mean opinion score, and objective differentiated grade. That was the scale that you see at the table, how it looked like. And the result of the subjective quality evaluation, including speech samples in the British English, German language, Polish language, and all is shown in the next figure. It should be noted that this result have been arrived at from the both communication direction, from the point A to point B, and from the point B to point E. And we will show for the we have the samples processed for the 8 kilobits per second. We will see the objective difference grade. If we change to the 16 kilobits per second, we have the better results, and the most better results is for the 24 kilobits per second. And something about the tests. When it comes to the background of tests, individuals, it is want mentoring than each one. The Polish was the mother tongue, where both English and German was the second language of choice, and microever participant pointed of the sequences spoken by a male lecturer seemed more applying. In our case, due of the profile of the mining industry, the feedback becomes an important factor. And the conclusion, as shown that on the presentation for the BPL communication, transmission can be effectively used in medium voltage cable networks for data transmission, especially voice communication, considered as so-called last chance in case of hazards and mine disasters. Such networks are theoretically the most resistant to mechanical damage. In order to provide high effectiveness of the BPA PLC transmission, particularly understandable voice messages, one needs to know to overcome the influence of the environmental interfering electromagnetic field, electromagnetic compatibility factors. Furthermore, the use of the affection coupling with the cables is on the great importance. And describe this test carried of the 6 kilovolts main cable line of approx 300 meters long have shown that the affection delays of the bidirectional voice transmission for both rate electrical cable operation condition as well as under extreme condition remains practically the same. We can see that the analysis show the speech signal at the lowest bit rate, 8 kilobits per second, provide to be insufficient in order to provide clear and unambiguous statement. Only in case of 24 kilobits per second, the voice transmission was clearly understood and acceptable. Similar results we are found with the having type of the coupling or node. And that is all. Thank you for attention.
Hello, Professor.
Hello, Professor.
Probably something went wrong with the computer or electricity again.
Okay. Okay.
So does Does anyone have questions? Okay, so if there are no questions, so I would like to invite the next presenter, and it will be Michal Pipiska, and the name of presentation: MOSFET gate resistance influence of voltage imbalance of two-switch feedback converter. So please.
Hello, can you hear me? Hello?
Yes, yes.
Okay. Hello, my name is Michal Pipiska and I'm from Uninterruptable.
Full screen.
Yes, wait. Presentation. Yes. Hello, my name is Michal Pipiska and I'm from Uninterruptable Žilina. This article deals about the two-switch flyback and some problem with imbalance of voltage on transistors. This is a part of our students, which is diploma thesis. So at first, they must design some converter which have this parameter: input voltage range 120 to 650 volts. The output voltage is symmetric, 15 volts, or 30 volts non-symmetric. The output nominal current 1.67 amperes and output power 50 watts, and switching frequency around 100 kilohertz, and required efficiency 9%. For a good choice of topology, we looked at the table, and here is some parameter, and our best choice for our design is here, where payout is lower than 100, input voltage is higher, and then 400 volts, and output current is lower than 5 amperes. We can see that we have a two choice: two-switch flyback and two-switch forward, but a better choice is two-switch flyback because two-switch forward is little cost and little complicated. So at first, I would like to explain how two-switch flyback work. In first interval, which is accumulation interval, is the transistor open, and the energy from the input is stored in the transformers, because on the second side voltage is in opposite way, so is blocked by diode, and in this interval is accumulated the energy to transformers, and the energy to the outputs going from the output capacitor. Second interval is the accumulation interval, when the energy from the transformers go through the diode to the output capacitor and the output. In this state is transistor off, and the voltage on this transistor is divided to the same value, and the value is input voltage plus reflected voltage, and divided by Q, and that is voltage on higher transistor and lower transistor. This voltage is theoretical same. Here's some simulation where is power stage and control stage. Here is a regulator, and here is transistor, freewheel diode, and transformers, output diode, and output filter and output. The result from the simulation is here, and you can see that the voltage on transistor is the same, and this is theoretical, but in practical is little different, because there is some parasitic capacitance of transistor, some leakage current, and ATC parameters, which create imbalance of the voltage. So one of the best choice of driver is here, when we use for driving transformers, and these transformers driving the both transistor in same time, and in this case it's not you have the same time, same switching time. So when come impulse from controller to the input, this transistor is open, and the energy going through the primary winding to the ground, and the impulse going to the secondary side, higher and lower transistor, and this transistor is open through the gate resistance for open. And when the impulse on the input is 0, this transistor is open. This transistor is open, and the voltage is will go from here to the supply, and the voltage on the second side is in opposite way. So this voltage is on this diode, and this voltage dissipation open this transistor, and this power transistor is switching off through this gate resistance. This driver provide the same time for open and closed, but this is still little problem because this transistor is in real not same, as have a little different parasitic capacitance and ATC. Here is designed converter. As you can see, here is input filter, driving transistors, higher and lower transistor, transformers, output diode, and output filter and output. You can see that if we use the same value for off-gate resistance, the same value, the result is different. That here is, you can see that here is drain source voltage and here is input voltage. So when we changing input voltage, the voltage on higher and lower transistor is different, and this cause different dissipation, and this cause higher temperature on one transistor because have higher power losses. And this happened when the resistor was the same. You can see that the lower transistor have a higher voltage in off state because it's little faster. So you can see here some waveform on transistor in off state, that you can see that a lower transistor have higher value, and it goes that is faster than higher transistors. So we make some experiment, and we change the lower resistance to the higher value, and this transistor make a little slower. In this way, we change the lower gate resistance to the 39 ohm, and this cause that the voltage has swap. So on higher transistor is higher voltage than lower transistor. So around, I think, 200 volts, and this too bad. So we make another experiment, and you can see here the voltage waveform on higher and lower transistor, and we make some next experiment, and we change the value of gate resistance of lower than the 30 ohm, and you can see that here is difference between voltage around 30 volts. So you can see that this is a little not same, but it's better than in first case or second case. So in this case is power losses little in same, but with different, but with little different. You can see here the waveform of in this case that the voltage is same. And here is full power and maximum input voltage. So we can see that here is in discontinuous mode that the voltage going to oscillation on drain source. Here's a thermal performance. So you can see the transistor have same temperature. If the power losses on one transistor will higher, the temperature of one transistor will be bigger, and that make can explode or damage of the transistor, because that transistor will higher temperature than in datasheet maximum temperature. And that's all for me, and thank you for your attention. Hello? Is there something? Someone?
Okay, probably Chairman. Yes, he has some problems. So unfortunately, he won't be able to complete. So I would like to ask if somebody has any questions from the audience. So if no, so we would like to thank you for the presenter. And session is finished. Yes. So thank you for all presentations, and thank you for attending the conference. Maybe next time we will back to more convenient form, yes, of the conference, as it was usually.
With another virus.
Also, if you hear me, thank you, and sorry for these breaks from my side. I had a lot of problems with electricity supply and now with internet connection and with everything. Thank you to everybody.
Thank you, Mr. Chairman. Bye.
Thank you. And see
Thank you very much.
Thank you. Have a nice day.
Have a nice day.
Thank you. Have a nice day.